My name is Haoyu Chen. Today, I'm excited to present our work from intention to practice towards systematic validation of NIDS rule enforcement. This is a joint work with my colleagues at Huazhong University of Science and Technology and Zhejiang Lab. First, let me start with some background introduction. Rule-based network intrusion detection system, or NIDS for short, plays an important role in cybersecurity. The way they work is conceptually simple. An NIDS uses DPI, deep packet inspection, to monitor network traffic and then matches that traffic against the predefined detection rules that capture the signature of known attacks. These rules may be written manually by users or selected from expert-maintained rule sets that are updated over time to cover emergent threats. Now, a typical rule has two major parts. The first part is the header, like the first line. It specifies which traffic should be evaluated. For example, it may define the protocol, source, and destination addresses. The second part is the options, the rest part of it. They specify how the traffic should be evaluated. For instance, they may say that the URI should contain a certain string or that the HTTP payload should match a regular expression. So conceptually, a rule expresses a detection intention that if these conditions should hold in certain network traffic, then the NIDS should raise an alert. However, rules are not always enforced as intended, which is the core observation behind our work. We see two broad sources of this gap. The first category is rule-related issues. Rules are highly structured. Even a small mistake can completely change the detection behavior. And once you have thousands of rules deployed together, interactions between rules can produce unexpected consequences. The second category is implementation-related issues. Even when a rule is perfectly written, the NIDS may parse the protocol differently from the actual endpoints, which lets malicious traffic slip through. In addition, complex regular expressions or worst-case string sanitization may cause timeouts or delayed alerts. The core problem is that there's no inherent guarantee that deployed rules are enforced as intended. This motivates our central question: how can we validate whether deployed rules are actually enforced as expected in practice? So existing approaches do not fully answer this question. One line of work focuses on static analysis of rule sets. These methods use theoretical models or formal verification to identify potential redundancies in rules. However, static analysis cannot catch implementation flaws in the NIDS. Even a rule set that is correct on paper may still fail in runtime. The second line is protocol-based fuzzing. Tools like Geneva and Bufas mutate fields inside specific protocols to test NIDS behavior. These tools are very useful in their own domains, but they don't target the detection rules. So there's very little chance that their generated packets will actually trigger the rules deployed in the NIDS. In short, existing approaches are rule irrelevant and they lack a systematic methodology. To address this gap, we proposed the NIDSFuzz, a systematic rule-oriented fuzzing system. NIDSFuzz solves three core research questions. The first question is, how to design test packet generation strategies that achieve comprehensive validation. Our key insight here is to make the generation rule-based rather than protocol-based. Specifically, we take the deployed rule set as input. It parses each rule and extracts the signatures that describe suspicious traffic. In our design, these signatures are represented as a data structure called buffer constraints. The buffer constraints are later used to construct the concrete packets like this. This gives us an important benefit. The generated packets are guaranteed to align semantically with the rule, so they will not be discarded prematurely by the NIDS. As a result, our system can provide targeted validation and systematic coverage of the deployed rule set. However, simply generating packets that match the original rule is not enough. To uncover issues, we need mutation. We designed 4 tailored mutation strategies, with each targeting a different class of potential rule enforcement issue. The first is the pass-through strategy. It simply translates the rule into a packet without any mutation. This sets a baseline. A rule should at least be triggered by its own unmutated traffic. The second is obfuscation strategy. Inspired by real-time invasion technologies, we applied transformations like character encoding and path shifting to the payload. This tests whether the NIDS can correctly normalize and match semantically equivalent inputs. The third is the repetition strategy. We repeat buffer constraints, either element-wise or block-wise, as you see in the figure. The goal is to stress the rule matching engine. This is useful for exposing performance issues, delayed alerts, and worst-case behavior in sanitization. And the fourth is the blending strategy. We pick multiple rules at a time and blend their buffer constraints into a single packet. This is how we surface issues like overlap and conflict across rules. Together, these 4 strategies cover a broad spectrum of rule enforcement issues. And the second question is how to efficiently inject this traffic into an NIDS. NIDS monitors bidirectional communication. It inspects both requests and responses, so we need bilateral injection. A naive solution is to just use real programs as endpoints. For example, we could use a real HTTP client and a real HTTP server. But this approach has 2 problems. First, the real programs process every incoming packets, generate responses, handle session state, and most of that work is wasted because we don't actually care about the application logic. We care about NIDS behavior. And second, a real program is not easy to control. It can be hard to tune the contents in the order of generated packets. So our solution is a tunable initiator and a tunable responder. This gives our system an efficient and flexible way to inject bidirectional test traffic. The third challenge is sanitization. Once we have injected test traffic, how do we identify potential rule enforcement issues? In traditional fuzzing, we may look for memory errors or sanitizer reports, but this does not directly apply to NIDS. And NIDS is transparent to endpoints. It does not interfere with the traffic. It only observes. So the only signal we have is the generated alerts. To align the test packets with the generated alerts, we propose a port-based alignment scheme. The tunable initiator uses a continuously increasing source port for each request. So when an alert comes in, we read its port field and match it back to the packet that triggered it. After alignment, we still need oracles. Oracles are some criterion that tells us whether a given alert pattern indicates a rule enforcement issue. We use differential checking approach. We deploy multiple NIDs in our experiments, all loaded with semantically identical rule sets. We feed them the same test traffic, and then we look for inconsistencies. The important idea here is that NIDSFuzz does not require access to internal NIDS implementation details. It treats the NIDS as a black box and uses alert discrepancies as signals of enforcement issues. Putting all of this together, this is the overall workflow of our system. It has 4 phases. First one is pre-processing, where we parse and select rules. Second one is generation, where the rule mutator and packet render turn rules into concrete packets. The third one is injection, where the tunable initiator and the responder send the bilateral traffic. The fourth one is sanitization, where the alert monitor and differential checker identify suspicious cases. The key design choice throughout the system is that NIDSFuzz is rule-oriented. It generates traffic based on the very rule set deployed, enabling targeted validation and systematic coverage. We evaluated NIDSFuzz on 3 widely used NIDS platforms, Snort 3, Suricata, and Snort 2, each running its latest version at the time of writing. For rules, we used the latest Snort community rule set covering 4 protocols: HTTP, FTP, DNS, and SIP. In total, roughly 4,600 rules. The network topology is built with Docker Compose. We have 3 subnets, one running NIDSFuzz, another one running the 3 NIDS instances, and the last one running the tunable responder. The whole environment is fully scripted, so everyone can reproduce it. NIDSFuzz reported over 10,000 unique rule enforcement issues in total. Through manual investigation, we totally identified 18 distinct types of issues. This table summarizes our findings, including the affected NIDS platforms, the affected protocols, and the security impact of each issue. We classified these issues into 2 broad categories. The first category is rule-induced issues, which originate from the rules themselves. The second category is implementation-induced issues, which come from the NIDS engines. In total, we identified 18 distinct types of issues. Let me walk through a few representative examples. Here present some examples. The first example is redundant sticky buffers. We found rules that contain the same sticky buffer twice. For example, 2 file data declarations in the figure. This works fine in Snort, but does not work in Suricata. Another example is misused keywords. For instance, some SIP rules use a PCRE modifier that's intended for normalized HTTP headers. This distorts the semantics of the rule. These examples show that rule writing is error-prone, and such errors can be exploited to evade detection. Here is an example of overlapping rules. We found many rules with highly similar signatures, which means a single crafted packet can trigger multiple rules at the same time. This can be exploited to launch squealing attacks, where a flood of false alerts overwhelms security operators. We also found many implementation-induced issues. For example, Snort 3 doesn't inspect HTTP responses with invalid status code, and Suricata can be made hung until timeout when fed a malformed content-less header. These issues can be exploited by attackers to evade detection. We believe the NIDS community should establish unified specifications and implementation paradigms. We compared NIDSFuzz with existing tools and datasets. Geneva is a state-of-the-art evasion fuzzer. It operates only at the transport layer, so it cannot exercise application layer rules. UFuzz is a general-purpose fuzzing framework. It can mutate protocol messages, but it does not generate packets from detection rules. The CIC-IDS datasets provide real-world attack traces. They are useful for evaluating intrusion detection model, but they cover limited attack families and are not generated to systematically validate rule sets. The results indicate that none of these baselines achieved more than 3% rule coverage. In contrast, NIDSFuzz achieves over 94% coverage. Finally, we evaluated the performance of our system. For generation, the pass-through strategy is the fastest, producing 20,000 test packets in under 7 seconds. The repetition strategy is the most expensive, about 90 seconds, because it dramatically increases the number of buffer constraints to be rendered. For injection, our tunable responder completed 20,000 request response cycles in about 8 minutes, compared to roughly 40 minutes using a real Apache server. And in conclusion, we presented NIDSFuzz, a systematic rule-oriented fuzzing framework for validating NIDS rule enforcement. It addresses 3 core challenges: the rule-based generation for guaranteed coverage, the tunable bilateral injection for efficient traffic delivery, and the differential alert analysis for accurate issue identification. Using NIDSFuzz, we have uncovered substantial numbers of rule enforcement issues. For more details, please read our paper. And if you have any questions, please contact us by the email. And here's the link to our source code. Thank you for your attention. I'd be happy to take your questions. Thank you.